Well, we're probably going to talk about probability today. Yeah. Now, what does probability mean? Well, it's when you try to figure out how likely is it for a certain event to occur. You know, it's Sunday, so the probability going to church is pretty high compared to Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, right? Although there may be other things going on other days, you know, the possibility of this outcome occurring, that's probability. Now, with probability, one of the things you see in your common everyday life most frequently that uses probability is shown in this picture. This is our Greenville weatherman there, John Cesarich, and Johnny knows weather. And he's showing the weather map. There's a radar. Looks like might be a little bit of a storm front coming in here in Greenville. And he might be saying something like this: tomorrow we'll have a 30% probability of rain. Now, what does that probability of rain mean? Does that mean that 30% of the day, of the 24 hours tomorrow, it will be raining? No, because sometimes you have the rain come through in narrow little bands that, you know, a front comes through, it's cloudy and it rains from 12 o'clock off and on till 4 or 5 o'clock in the afternoon, and then the rain's gone. You know, so that doesn't necessarily mean 30% of the time. Well, what does it mean then? How about 30% of the area? You know, in our upstate of South Carolina, 30% of the viewing area of the meteorologist giving out his forecast, 30% of the area is likely to get some rain. Okay? Another way to say it would be like this. Okay, here you are right at your house. If somehow we could have 10 storms come across exactly the same amount of rain in the clouds, same wind speed, I know that's not possible, but just pretend. If we could have 10 of them come across, 3 of the 10 would drop rain right on your house. That's what they're saying. There's a 30% chance. So 3 out of 10 times, if an identical storm was coming across, you would be likely to have rain falling in your yard. Okay, now, I don't know if you've ever seen it, but it happened once. I can still remember. It was like, what? Up in Pennsylvania when I was a preteen and lived in the suburbs of Pittsburgh, that I was riding my bicycle and I looked over on this side and down the yard and over there. It was raining. And it wasn't raining where I was, and it wasn't raining over there. Now, with the isolated Florida thunderstorms that I saw as a teenager, that happened, oh, I don't know, several times a summer, where you could literally see rain on one side of the road, I mean falling wet over there and dry over here, because it's just a heavy cloud. So, you know, that's what we're talking about. What's the probability of getting wet? Right there, okay? So probability, if I were to give you kind of an explanation of it, is the ratio of the number of ways that it can successfully happen to the number of outcomes. So in our rain probability, the idea of my yard getting wet, that's success. Now, you may not think it's success if you're trying to have a pool party or something like that in your yard, okay? But if you're trying to wet and, you know, moisturize the ground and everything, then yeah, you want that. So, you know, 3 out of 10 times. And we often express that probability as a percent. So that would be our 30%. Well, is it always weather? No, it's not always weather. Something else that you have seen, probably, assuming you play some board games or have played them when you were younger, is something that looks like this. A spinner. Okay, now this spinner is divided into 5, technically the word is a sector, 5 pieces, 5 sections, 5 sectors, and you notice each one of them is about the same size. It's not like one is narrow and the other one is wider. Okay, if we have a fair spinner, that doesn't mean you go down to the fair. No. I don't mean a spinner at the fair. I'm talking about equal, even, fair. It's not biased towards a certain number. Okay, a fair spinner has to have each number, each sector, be the same size. And then it has to be able to spin freely, so that it doesn't have a little bump on this number, because then if it was going slowly, it would tend to stop in that number and not get to the next one. That wouldn't be fair. Now, I don't mean, that's not fair, Mom and Dad. I mean, it wouldn't be equal, even. And in a fair, equal, even spinner, there would be an equal probability of getting the 1, 2, 3, 4, or 5. So again, how do we explain that? How do we define that? Well, suppose I was trying to get whatever number it was, a 1, a 2, a 3, 4, or 5. Look again at the formula. What does it say? Successes out of possible outcomes. So that means if I spun the spinner 5 times and I was trying to get a certain number. For example, suppose I was trying to get a 2. If I spun that fair spinner 5 times, now it doesn't necessarily work out this way in small number of spins, but if I did, what I should see is a 1 one of those times, not necessarily in order, probably not in order, a 2, a 3, a 4, and a 5. Now, usually you have to get a big sampling. So if you want to really come up with that one success, I got 5, out of 5 spins, 5 possible outcomes, 1 out of 5, 20%. To do that, to get actually 20% of the time, you may have to spin it 50 times. And then 10 out of those 50. And that still may not, it may be 9 out of 50, 11 out of 50. Don't expect it in real life unless you do many. I mean, I'm talking hundreds and hundreds and hundreds of spins to come up with almost exactly the right amount. In small numbers, it is very unlikely. You have to have large, they call them population samples. So if you spin the spinner 1 time and you get a 5, could you spin it the 2nd time and get a 5? Yeah, exactly. And hey, this isn't in the section, but just listen. What was the probability of getting a 5 the first time? If it's a fair spinner, 1 out of 5. Remember our law of counting? What if I spin it again? 1 out of 5. What's the chance of getting 2 5s in a row? 1 out of 25 times. So that means that on a basis of a long, that wouldn't be 1 out of 25, it might be 100 out of 2,500. But if I went through 2,500 times spinning it twice, spin it twice, spin it twice, then theoretically 100 out of those 2,500, I would get 5 and 5. Okay, you can do all. You can take the formula we had for fundamental principle of counting. You can apply that to this too. That's not in your book. Okay, so the probability here is a 1 out of 5 or 20% chance of getting any particular number. Now, what about this question? A fair spinner, numbers 1 through 5, what is the probability of spinning an odd number? Well, the odd numbers are 1, 3, and 5. and 2 and 4 are even. Now, by the way, don't put the numbers up here. Okay, it's how many numbers. Okay, so what I want to put up in the top, how many numbers are there? Of the 5, there's 5 possible outcomes. How many of these 5 numbers would be a success? Well, 3 of the numbers, 1, 3, 5. 3 out of 5, and that would be 60%. Okay, so there's a 60% probability, if I spin it enough times, that I'm going to get an odd number. Now, I could spin it 2 times and come up with an even number both times. But if I keep spinning and spinning and spinning and spinning, eventually it'll come close to 60% odd numbers. Now let's go ahead and back up to this question. And I want to emphasize, I said it, but I really want to emphasize this because this is a mistake you could likely make. 5 numbers, fair spinner, find the probability of spinning a 2. Okay, so I want the successes over the possible outcomes. Okay, well, I know there's 5 numbers. That's easy. Okay, find the probability of spinning a 2. So success is when I get a 2. No. No, 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 no. The question here, it's the number of successes out of the number of possible outcomes. There are 5 possible outcomes. How many of the 5 numbers are 2? There's only 1 2 on the spinner, right? The spinner had 1, 2, 3, 4, and 5. There's only 1 2, so there's 1 success. If I get a 2, that's my success. If I get a 1, 3, 4, or 5, it is not a success. So there are 5 possible outcomes, but only 1 success. So be very careful that you do not put the item, the number, the value you're looking for. Be sure that you put the number of times it could happen. In your numerator and your denominator, number of times that I could get this, it will be a success out of the total number of possible outcomes. Okay, so be careful. It's a very easy thing to do, to put the wrong number, not the value, but the number of times that I could get a success out of the total number of outcomes. Let's go ahead and try the spinner. We have this game spinner here. If you notice, it's a little unusual. What does it have? It has 1, 2, 3, 4, 1, 2, 3, 4. So if I was trying to get a 1, how many different places could it land, on the pointer and have a 1? Well, there's this one and this one. There's 2 ways to get success out of how many? Well, there's 2 out of 8. Now, I can reduce that down to 1 out of 4. But technically, there's 2 successes out of 8 separate outcomes, because I've got the blue one and the yellow one. That's different. There's a green 2 and a purple 2, and so on. So there are technically 2 ways to win out of 8. All right? Let's see, just for fun. We're supposed to get 2 out of 8, which reduces down to 1 out of 4, for our number 1. Let me spin it, and let's see what kind of distribution we get. Now, the numbers are spaced evenly, but is the wheel, the spinner itself, is it fair? Does it have a bump? Does it catch somewhere? Don't know. But if you do spin it enough times, and we won't do it dozens and dozens of times, you would catch that. Okay? We're looking for a 1. Hey, I got one. How about 2, 2, 2, uh-oh, 2, 4, 1, 3, 3. Now, can you hear something? That one we're going to say is on the line. We're not going to count that one. It was really close. 4. You hear the as it's rubbing. So the fact that it's rubbing at certain spots, it may not be an extremely fair spinner. Now I have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times that I spun it. And I had 2 1s, 4 2s, 2 3s, and 2. So, yep. So it went 2, 4, 2, and 2. So that meant I came up with 20% 1s, 2 out of 10, 40% 2s, 4 out of 10, 20% on the 3s, 20% on the 4s. So on our little sample of 10 spins, it doesn't seem like it's exactly fair. But I noticed that when I was spinning, that it tended to, hear that? Tended to catch on the green 2. And since when I spun a green 2, you hear how much it slowed down? If I didn't give it enough to get past it, it would stop there. And that's probably the reason why I had 2, 2, 2, 2. So it's probably not an extremely fair spinner. And you'd want to be careful of that if you were playing a game. How about this spinner? Is that fair? Well, only if you're supposed to get 1, because you notice the 1 is as big as the 2 and the 3. So I would not expect to get 1 1/3 of the time. I mean, actually, if you figure out the percentage of a circle, 1, I would expect a 50% chance on 1, and about a 25% chance on 2 probability, and a 25% probability on 3. Okay, so those are just a few spinners and how it works, just to put it some actual probability to the test. Now let's talk about this possibility of probability. Okay, we have this situation. If trailer license plates have 3 letters, just for sake, okay, with no repeats, find the probability of getting a license plate that has letters from only the first half of the alphabet. So remember, we want our success out of our possible outcomes. Okay, so we have to have 3 letters, and we have to use our fundamental principle of counting, that we're going to multiply them together. Now, the first half of the alphabet, that's A through M, there's 13 letters. So I want 3 letters for success from the first half of the alphabet. There's 13 to choose from, and it said no repeats. So 13, that leaves 12 letters left for the second, 11 letters for the third. Now, how many possible outcomes are there? What are the choices of all the letters that could be first? I don't know. Well, how many letters are there? 13. No. Possible, not success. 13 is the first half of the alphabet. That's success. How many total letters are? Oh, well, there's 26. Right. So there could be 26 in the first slot, and then what? Yeah, 25 and 24. Okay, now that ends up with 1,716 over 15,600. And believe it or not, that actually reduces down to 11 over 100, which is going to come out to be 11%. Yeah, so there's just over 10% chance that the first half of the alphabet will be in all three of the letters. So you'll get an A, B, C, A, C, D, and so on. What if I change that? What if I say that has, what if I change it to has only vowels? How many do only vowels? Well, I would have, how many vowels are there? A, E, I, O, U. 5. So for my success, there were 5 to choose for the first letter. There's 4 to choose for the second letter. There's 3 to choose for the third letter. There's 5 vowels, there's 4 left, there's 3 left. And then the denominator is going to be the same. There's still 26 letters, 25 letters, 24 letters in the alphabet. So I'm going to get 15,600. 20 times 3, 60. So that means I need to take 60 and divide it by 15,600. Oh, and by the way, that reduces down if you want to do that. That'd be 1 out of 260. And that's just a little under 4%. So there'd be a 4% probability of getting a license plate with 3 vowels. There's just one more thing we need to talk about, and that is called reliability. What is reliability? It is the reverse of the probability of failure. Huh? Okay, how about this? If I tell you there's some action, whatever it might be, and it has a 5% probability of failure. You're trying to do some task, or you're trying to maybe have a lawnmower cut the grass and the engine might fail. That 5% is way too high. I mean, 5% would be 1 time out of 20 I go to cut the grass and the engine won't start. Well, maybe it does work that way if your lawnmower is old. But if my probability of failure is 5%, here's the thing we need to concentrate on, then the reliability is 95%. So there's 5% that don't make it, then there's 95% that do. See, that makes sense. One last thing to point out. What if there are a chain of events and we know the probability of failure of each one of those, or the reliability? You can do it either way because it's so simple. If one's 5, the other's 95, okay? How do we figure out the reliability of a chain of events? What have we learned? What does the fundamental principle of counting tell you? Multiply those. That's our big overriding fundamental principle. So, for example, if I have this car, okay, and this car has a 97% reliability of its fuel pump over, say, 50,000 miles, okay? The ignition, 98% reliability. The engine, 95% reliability. The transmission, 97% reliability. Well, if I want to know what's the reliability, let's say that's all that could break down in a car, it isn't, then I need to multiply, and I'll put it as a decimal, 0.97 times 0.98 times 0.95 times 0.97. and I multiply that all together, and I get about 0.88, or 88% reliability. So in what I stated at the beginning, that will mean that 88 out of 100 times, or 88 out of 100 of these cars, would run the 50,000 miles without any of these failures. Okay, and that would also mean, if you turn it around, the probability of failure is 12%, or a little over 1 out of 10. So if there were 10 people in your town that had that same car in 50,000 miles, about, on average, and you saw it doesn't always work that way with a spinner, but on average, 1 out of every 10 of those would need some repair during that 50,000 miles. Do you see all the different things you can do with probability? Well, there's a lot. And I like playing with numbers. You may not, but at least now you know a little bit more about how to do that.
Why is insurance so important? And how exactly does it work? Well, having insurance is important because accidents and emergencies are a part of life. Natural disasters like tornadoes, hurricanes, or floods can cause a lot of damage, and a hospital visit is expensive. So it's good to have insurance and be prepared for accidents and emergencies before they happen. But how do insurance companies know how much money to have available or how much to charge for their policies? After all, they need to know how to plan ahead too. That's where actuaries come in. They're risk management professionals, which means they know a lot about the probability of something happening. How do they know the future? Well, they don't really. Actuaries are just experts at statistics, which is math that uses formulas and research to calculate the probability of something happening. For instance, by looking at data about the environment, they can estimate how prone a city's buildings are to fire, flooding, or even an earthquake. Actuaries are kind of like professional advisors. Insurance agencies will usually have at least one actuary working for them to give them advice about how much money they need to keep handy in order to pay claims. Actuaries also suggest what kind of investments to make, since you can apply statistics to investments too. Not only do actuaries work in insurance, they're also employed by financial companies, investors and accountants, as well as the government and the healthcare industry. Actuaries couldn't do their job without excellent math skills. They help a wide range of companies and organizations plan and prepare for the future. Even though it's impossible to know for sure what will happen, it's always responsible to do what you can to plan ahead.